The framework I developed in the last screencast is based upon a very simple model of walking. We're going to start off with very simple movements and introduce more complex movements sequentially. Before proceeding though, I want to talk a little bit more about what I mean by modelling. A model is something that represents reality in some way. The model is always simpler than reality though, and in biomechanics this is the model's great power. Reality is just too complex to understand, but because the model is simpler, we have some chance of understanding it. Modelling thus has a number of stages. The first is to make sufficient simplifications and assumptions to be able to understand what is going on. In the case of understanding human walking, this requires considerable simplification. It's important that we write down exactly what those assumptions are. For a model to be useful, we should be able to specify its characteristics completely. Models can either be descriptive, they simply allow us to describe what is happening in the context we are modelling, or predictive, they allow us to predict what might happen in other contexts. Predictive models are much more powerful. One of the reasons that they are so powerful is that they can be tested. We can predict what should happen under specific conditions, then test those predictions against experimental data. A good model allows us to understand something about reality that we couldn't otherwise be able to, and leads us to predictions that can be tested. We're going to use a model I've called Vern, after Vern Inman. When I first gave these lectures, I gave everybody a cardboard cutout model of Vern. Goniometers are presented on his hip, knee and ankle joints, which enable you to understand exactly which angle each joint is at when Vern is manipulated into different poses. If you think this would be useful, you can download the template at my blog and make one up. I've now developed an electronic model that I call eVern. If you're looking at this in PowerPoint, you should be able to move the model by dragging with a mouse on the different segments. If you're looking at the screencast version, then you'll have to go to my blog before you can do this. Having got used to the model, we can specify the assumptions. The most obvious is that we are working in 2 dimensions. Most of the action in walking occurs in the sagittal plane, and we'll focus on this in the screencasts. The second assumption is that the human body can be modelled as a number of rigid segments. The third assumption is that the segments are linked by simple pin joints. And the fourth, which follows from the third, is that joint positions can be specified as a simple joint angle. There are a couple of specific things we should just bear in mind. You'll notice that the green arrow that we use to specify hip flexion isn't vertical. This is because, in gait analysis, we assume that the transverse plane of the pelvis is that containing the anterior and posterior superior iliac spines. This plane is tilted a little forward to the horizontal, and thus even when the trunk and femur are both upright, we still record about 14 degrees of hip flexion. Notice also that the line on the foot is perpendicular to the plantar surface. In gait analysis, it is the angle between this and the long axis of the tibia that we use to define dorsiflexion and plantarflexion. When the ankle is in neutral, we refer to dorsiflexion and plantarflexion as being 0 degrees.